All right, let's go ahead and get started. So today is the third day of our lab, and we've just recently done with the coordinates and time part 1, part A, which was the time portion of it. And today we're going to go over the coordinates. Again, I have your labs from last week graded, and I have the new lab handouts for you today. And after the intro lecture, we'll get straight into it. So coordinates and time, when you have, let's say you have a coordinate system, the whole point of a coordinate system is to find the position of something. If I know where something is, an object is in space, I can tell someone where that is by describing, oh, it's next to, my computer is next to this window or whatever. But that's kind of relative, it depends on where I am in respect to the computer. But if I know that there's a coordinate plane that is covering this entire plane here, and I say, okay, well, it's at this x and this y, then anybody in any position can find out where my computer is just based on the coordinates that I've given them. And so that's the whole point of the coordinate system. And on Earth we have this. We have our terrestrial system, which I went over briefly last time with the latitudes and the longitudes. So the latitudes are going to run from east to west, and they follow along the same orientation as the equator. And the equator lies at 0 degrees latitude. And you go from 0 to 90, going upwards towards north. So you have 90 degrees north is going to be our north pole, and 90 degrees south is going to be our south pole. So those are the latitudes. And likewise, perpendicular to that, orthogonal, you have the longitudes. They run from north to south, and they go along the same path as the prime meridian, which is the international date line, as was discussed last time. There are 24 lines of longitude that make up the globe, the coordinate system, the terrestrial coordinate system for the Earth. Here's another image of our terrestrial system, and as you can see, it creates a grid. The longitudes and the latitudes create this grid that allows you to pinpoint exactly where you are. Say you want to talk about, well, where's Los Angeles? I think it's 34 degrees north and 180 degrees west. So you would go 30 degrees up. This is 30 degrees, so 34 is maybe a little bit above that. We know where Los Angeles is right around here. And it's not labeled here, but the 180 degree would be, 118 degrees for Los Angeles for the longitudes. Now another coordinate system is the horizon system. So now we're getting into, okay, well, the coordinate system for the Earth, that the terrestrial coordinate system, that's good for determining where something is on our Earth, where a city is or where a country is or whatever. Well, when we want to talk about where a star is, you have to have a different coordinate system. You have your horizon system. This one is completely relative to where you are. It's all about where you are, the observer. That determines where you see an object. If I see the clock there, there's a couple of ways I can describe that clock. You have the azimuth, which is the angle going outwards this way, in plane with the horizon, right? The horizon is the horizon. It's what makes up this plane that I see as the observer. And the azimuth is the angle from, goes in the eastward direction, starting at north. That angle is going to determine where my azimuthal angle is. So, I don't know, does anyone know where north is pointing here? It's that direction? All right, so if that's north and I want to talk about that clock, straight north is going to be 0, so it's going to go, almost not quite 360 degrees, maybe 350 degrees. So that's going to be my azimuthal angle right there. And then I need an altitude angle, which is going to determine the height from my horizon up to where that place is. And that's going to be another angle from 0 to 90 degrees, being completely perpendicular to me. I'd say maybe that's about 30 degrees. So I could say that clock to me is 350 degrees azimuthal and maybe 30 degrees in the altitude. But that changes depending on the perspective, right? So So if one of you were to look at the clock, it's in a completely different position. It's no longer going to be that 350 degrees in the azimuthal direction. It'll be entirely dependent on where you're observing it from. The zenith is the point directly above you, and the nadir is going to be the point directly below you. Those are completely, again, relative to the observer. And they're not necessarily going to be north and south, right? Like if you are on the equator, your azimuthal angle, or your zenith, is going to be directly above you, but you're on the equator. So this is the equator, and this is the North Pole, right? And now you're standing here on the equator. Your zenith is going to be out here, right? It's not going to be the North Pole at all. So again, it's completely dependent upon where you're standing and where you're observing from, as you are you create the coordinate system. So here's another image of the horizon system with the zenith. These are some stars. You have the Big Dipper constellation here, Ursa Major. You have your Polaris, the North Star, Venus planet. And you can determine these altitudes, again, going from your horizon up to where the star is relative to you. So the altitude for this star here in the Big Dipper is going to be about 30 degrees. And the azimuthal angle is going to be 330 degrees, starting from this north position, going all the way around, and not quite making it to 360 degrees. Just like the clock wasn't quite 360 degrees, but it was pretty close. So these are the two angles you would just use to describe where this star is relative to you, the observer. But if I'm looking at it from a different perspective, again, your angles aren't going to mean much to me because the star is going to be in a completely different position. So that's one of the drawbacks. Yeah, that's the drawback to the horizon system, is that it's completely relative to the observer. So what if you need a system that anybody can use from any perspective, that is completely unified, just like we have the coordinate system for the Earth, going back to the terrestrial system. This works anywhere. If I'm somewhere off in a different country, I can just say, well, this is the coordinates of Los Angeles, and anybody in any part of the globe can find where that is on the map. So likewise, we want a system that we can use to describe any star from any position, and everybody will be happy because everybody gets to see the same thing. And that is going to be our equatorial system. Now, this all surrounds this celestial sphere. So the celestial sphere, which is this image here, and it's also this object here, is going to be an imaginary sphere that is expanded outwards from the Earth, right? And all right, it's an imaginary sphere that is expanded outwards from the Earth, and it has lines of longitude and latitude. They're called different things, which we'll get into in a second. But as the image shows, it's an expanded sphere, and what it is you can imagine that all the stars and all the objects in the night sky, all the celestial objects, you can imagine them projected onto this sphere. And obviously they're not all on the same plane, because all the stars are at different, they're different distances, right? So while all the stars in the night sky might look like they're all on the same plane, they're not. There's definitely different distances as you go out. So you can just imagine, though, that it's all on this celestial sphere. The celestial equator is the same. It's just, imagine the equator of the Earth just expanded out and mapped onto the celestial sphere. So it follows in the exact same plane. And here you have the ecliptic, which follows a different plane. Ecliptic is, if you imagine the sun going across this, the sun follows this path on the ecliptic. Now it really doesn't, because the sun doesn't revolve around the Earth at all. But this doesn't orbit around the Earth. This allows you to see the day and night cycle, right? When it crosses this plane, when it crosses that equator, the celestial equator, when the sun goes above it, then you're going to have your daytime, and when it goes below it, you're going to have your nighttime. And when it hits, those are going to be your sunrise and sunset. Yes. So here's the equatorial system in a different light. These are the line of declinations. It's going to be your latitudes, the latitude lines, going from east to west. Yeah. And the right ascension is going to be they're going to be the longitudes, right? They're going to be going these direction here, straight up and down from north to south. The declination angles go from 0 degrees at the celestial equator, and they go up to 90 degrees at the celestial north pole, the north celestial pole, down to 90 degrees at the south celestial pole. The right ascension lines are going to be measured in hours. They measure from 0 to 24 hours. And as I said before, the Earth rotates 360 degrees in one day. So that's 360 degrees in 24 hours. That's 15 degrees per hour. So each line across, that's 2 hours, so that's about 30 degrees, right? And so each one is split up into 12 different sections of these right ascension lines. And it increases as you move eastwards, the right ascension. And here is what it all comes down to. You have your star chart, and you want to find an object in the sky, and you know the coordinates of it, you know its declination, you know its right ascension. Well, you can go here, and you can look. You can't see, but I have one for you all. It's going to be on the printout. You would pick your time, your right ascension, however many hours, and then you can pick your declination, and then they're going to intersect at wherever you're looking. If you want to look at this constellation here, that's you need the you're going to need your declination and your right ascension to find out where that is. Yeah. So that's about it. Whole point of the coordinate system, the whole point of the celestial sphere is to find objects like that. This would be mapped on a celestial sphere. You can imagine this is a 2D image of a 3D projection, but it allows you to find where objects are in the night sky that is not relative to one observer. It can be anybody. All right, well, I posted this on the Moodle already this time, so you can go ahead and pull it up if you need to. You'll probably need it for the lab, which I will hand out now. And then I'll hand back the previous lab as well.
Can you help?
Yes. With
Like passing the labs?
I'm sorry?
The labs.
Oh, did I help passing the labs? No, I'm all right this time. I got it. Thank you. I'm going to use your technique of patting down.
There's only beside yourself to go to people that are seeing you, and we sit opposite to each other. We turn and work out with action and brightness. Yeah, she said on the other side, it's an answer, and the other one says there's no answer, it's a free here. But Jordan doesn't know because the two right here, there's things crap. There's the visual sections. So I'm just
like right Ascension is our tower.
Is everyone able to pull up these slides on the move?
Yes.
Sick.
I don't know exactly what you want from us for number one.
Number one.
oh, nice.
Compared to Earth's coordinates, right Ascension is like. Well, the Earth's coordinates system, you have the longitude lines and the latitude lines. Well, likewise, the celestial sphere has the celestial coordinates are going to be the right ascension and declination. So which one is like which?
Oh, longitude and latitude.
Yeah.
Oh, okay.
Which one is which?
Okay.
Yeah.
Okay.
Yeah.
That makes sense.
Yeah.
That makes so much more sense.
All right, I'm going to pass back the labs from previous time. Just a note on the labs. I required calculations for each part, and basically, just if I found that there was no calculations or what that I found that there was no calculations that I just took off half points. From now on, if there are no calculations, I'm going to take it's going to be no points. I was being lenient this time, I only took off half credit for no calcs. But next time, but don't worry about it too much. Not really having too many calculations. There are 2 problems on this lab that are related to the last lab. So I need full calculations for those 2 problems. But yes, that's what I said about the lab. Flores, Miguel Flores. Sanchez. Bala. Ishan Bala. Sovian. Jake Sovian. Vasquez. Garcia. Joel. Castillo.
Oh, that's it.
Ortiz. Alvalza. Ayat. Yes. No, that's all right. Just try to get here. That's fine. No doubt, it's all good. There's 2 left? Okay, so I put the slide on.
I saw
All one story. That's all one story. Gustavo. Arroyos. Pretty organized? Money? Mariah's? Is that one or two? Did I need two eyes? Did you, is it just the wall or did I need two eyes? Martin? Timothy Martin? Cervantes? Hernandez? Jacob? Home Jacob? Hops. Max Hops. Hops. Solano? Martinez? Sebastian? McAllister? Poe? Grissom? Red Grissom? Martinez? Lee? Fong Lee? Spellman? Markswalk? Onyango? Riz. If there's anyone that didn't receive a lab back that was here last time, I guess I have a couple here left. Just come to me. I'm assuming they're absent today. Let's try these. Chronocrite? Gonzalez? Gonzalez?